Today, we're gonna be flying the DJI L2 LiDAR and the Rock R3 Pro LiDAR on this urban landscape behind me. I wanna compare the two LiDARs at 150 feet AGL and see how well they pick up things like curbs and fine details from that high. We're gonna go ahead and talk about the mission plan really quick and then get up in the air and compare those two data sets. Let's fly. But before we start mission planning and get in the air, let's talk about a little bit about the technical differences between these two LiDAR systems. And really, it's a story of accuracy versus range. So let's talk about the accuracy of the R3 Pro, the laser, versus the accuracy of the L2 laser. So the laser on the R3 Pro does about 0.5 centimeter precision. That's the ranging measurement from the laser. And this has about 2 centimeter precision for the ranging precision on that. And then when we look at the IMU specs, after the post-processing with DJI Terra, your heading is about 0.05 degrees accurate, and the pitch and roll is 0.025 degrees accurate. Now to contrast that, the heading is 0.03 accurate, so 0.03 versus 0.05, and the pitch and roll is 0.006 degrees accurate. So a much more accurate trajectory, accurate ranging information is coming from this. But where does the L2 really stand out versus the R3 Pro? And that's in the range. So the actual maximum range, they say you can go up to 450 meters away
at 50%
reflectivity. That means if the object is brightly reflective for this 905 nanometer laser, you can see it at 450 meters away. That's super far. In contrast, the R3 Pro at 10% reflectivity, we don't really say to go above 100 meters with that. So that's a huge difference. 450, 100 on the range. But the accuracy, much higher, and then not as high. And then we have the returns. This one does 5 returns, this does 2 returns. So more returns, more range, more accuracy, and more precision on the trajectory and IMU. Now, what else are the big differences between these two systems? Well, we have the camera on board. This has a 20 megapixel, this has a 26 megapixel, so a little bit better camera. More resolution on that. And now talking about how many points per second you get. This is 640,000 points per second, and this one does 240,000 points per second. Now you got to multiply that by the number of returns. The total number of measurements you could potentially possibly make would be 5 times that 240, so that's around 1.2 million, I think. And this one has 2 returns, so you would multiply that 640 times 2 and get 1.28 million returns. So similar if you were able to get all the returns. Now the other difference is this is a 360 degree scanner, and this one has I believe it's 70 degree field of view. Check me on that one. So those would be the other major differences. And then this only works on the DJI M300. This works on basically any drone that can carry the weight. It's 1.2 kilograms in total. It also has the SLAM capabilities and mobile mapping capabilities. So adding those into it makes it a different product on those sides. So yeah, but again, today we're gonna fly this urban environment, and what I'm really curious about is seeing how well does it pick up the fine details. How well is the L2 gonna pick up curbs, and how well is it gonna pick up, all these other kind of really sharp details that you wanna pick up from your LiDAR data in an urban setting if you're doing things like planimetrics or trying to pull out that CAD work from the 3D model that you're capturing. Okay, let's go ahead and talk about the mission plan we're gonna fly today, and then we will get up in the air. Okay, so I'm in the car. I just did a mission plan for this area behind me. We're gonna fly at 150 feet, so that's about 44 meters high. And then we're gonna fly at 4.4 meters per second. That's about 15 miles per hour. And then I'm trying to do 50% overlap on both. So here's the mission plan you can see here. And we're we are gonna fly the same mission plan for both LiDAR systems to get a real apples to apples comparison. All right, let's go ahead and take off. First up is the L2. Let's fly. Mission complete. Now let's get the R3 Pro on and start flying. Next up, R3 Pro. Let's fly. All right guys, we just finished flying the R3 Pro and the L2 on the site behind me. Now let's go back to the office, process data sets, take a look. Let's go. Okay guys, welcome back to the office. Now we're gonna dive deep into this L2 data versus the Rock R3 Pro V2 data. Now we're gonna cover a few things here. I'm gonna cover the colorization. I'm gonna look at the accuracy of that. Then we're gonna look at the precision of the point clouds, some of those fuzz, and compare the two data sets. And then I'm gonna look at some of the alignment issues I found while I was exploring these data sets. And then after that, I wanna go ahead and start comparing different features of the L2. And I actually went back out and I flew two more missions, one at 120 meters and one at 30 meters, so about 100 feet. So 400 feet, 150 feet, and 100 feet, because after I started doing this analysis, I started seeing some weird things, and I wanted to go back out there and just double check to see what's going on. So let's dive into it. Let's get to the bottom of this and let's see what the accuracy of the R3 Pro V2 versus the L2 looks like in real life scenario. Let's jump in. Okay, so here I have the L2 dataset and I have the R3 Pro V2 on the Rock Cloud pulled up in the same project. It's the same area. So first up, let's take a look at the L2 and look at the colorization. So I'm gonna zoom around and just give you a general impression of it as we move around the data set. So I like to look at this area. It's pretty, you know, some construction materials in the back. Then we have the paint striping here, some cars. And let's go ahead and flip over to the R3 Pro V2. Now what I noticed right away on the R3 Pro is that much more fine detail is recorded. So looks a little bit darker, but also I see a lot more fine detail. I'm gonna zoom in on these paint stripings here actually. See the handicap, the parking. Now let's go ahead and flip back over into the L2 and see the difference here. So it looks just much more, less precision, less fine detail. Now, I'm also seeing a lot of mismatch here, and this happens all over the data set on the L2. And again, I ran this without optimization and without smoothing. I wanted to see the raw comparison of the R3 Pro V2 versus the L2. But at the end, I am going to go through the optimized and the smoothing and show you what those do, as well as flying at different heights. Because after I saw this, I needed to do some more investigation. Okay, so just looking at the colorization, much difference in the two systems, and as well as the accuracy on the ground. So again, coming back over to the R3 Pro. So much more crisp, much more fine detail. So that's on the colorization. I think the R3 Pro looks much better in my opinion. As well, it's definitely more accurate. So that's not even an opinion. It just is more accurate. And then the just blown out nature of the L2, you know, it's got like a Gaussian blur or something across the whole thing. So it looks a little fuzzy, like I'm in a hazy state or something, you know, kind of sleepy. Okay, next let's go ahead and look at the point clouds and see the relative fuzz from one to the other, just to get an idea of what the precision is from this 150 feet down to the ground. Now to do that, let's go ahead and switch over into the intensity gradient, because what I want to see is different reflectivity of objects. So we have like sidewalks, we have the blacktop, we have the paint striping, and you can see, you know, the more reflective objects are showing up as brighter colors here, as one would expect. That's how the color scaling is here as well. So dark blue is less reflective, red is most reflective. And so what we expect to see is in things that are red would be a little bit more accurate than things that are blue, just because of how the uncertainty with less light makes the measurement less. That's just an always thing. So darker things will just be less accurate inherently because of the way LiDAR systems all work. So let's come over here and look at the sidewalk. Actually, I'm going to go ahead and flip over to the R3 Pro as well, so we can see the intensity gradient on this. And I went ahead and came over here on this sidewalk, and I have a sidewalk and some blacktop. And what I want to do is draw a cross section here and then compare the two data sets. To get a good comparison, I'm going to go ahead and turn on single color. So let's make the L2 red and we'll make the R3 yellow. Great. And if we just empirically kind of look down the data set and just see what's going on here, we see that the L2 is always above and below, and so it's more fuzzy, less precise than the R3 Pro. So we can already start telling, just looking at this, you'll go anywhere in this data set and you'll see the same thing. The L2 is going to be less precise, and that's what the specs would tell us at the beginning of the video. I talked about the specs. That's what, you would read from that. But let's see what it actually translates into the real world. So I'm going to go ahead and open up that cross section. It's a 10 centimeter cross section, and let's take a look. So again, we have the L2 in red and the R3 Pro V2 in yellow. Now, if we zoom in, and let's just go ahead and this is a 10 centimeter width, a little cross section on that sidewalk. And let's try finding points that are right on top of each other so we can get a good instinct of what the precision is of the data. So it looks like on the yellow, these 2 points look kind of pretty much on top of each other. So we can look at this as 0.881. You see how they're on the left on that Z. So 0.881, I'm going to subtract off this one below it. 0.892. That's about 1.1 centimeters. And in the same area, now this we can measure from here to here, but then let's also do this one because this looks a little bit more representative of what you're going to see. So we'll do the extreme one first, and then we'll do the not extreme one. So extreme one is 0.856. 0.856. I'm going to subtract off this 0.926. So that's about 7 centimeters there. But then if we do this one to this top one, so that's going to be 0.911, subtracting off this 0.856. And that's about 5.5 centimeters on that one. Now, I went ahead and went through these data sets, and what I found was that the L2 is pretty consistent at this 5 centimeter range, but then there's some areas that really make it go worse to that 7 centimeter, even to 8. And let me show you that right now because it's pretty pervasive all across the data sets, and it's a consistent thing. And that's basically, I'm going to go ahead and show you GPS time. So here, this is the GPS time of the flight path of the L2. So you can see if I move this is how we flew, boom, boom, boom. And what we're actually seeing is that at the edges of the swath, so at the edge, it gets just much thicker. So that's what this, you see this yellow right here, that's the edge of the swath. And if I zoom in on this, you'll see like it just gets much more thick. You'll see the yellow looks almost like a wave cresting on the rest of the data set. So if we go ahead and draw a cross section on this overlap section and take a look at that really quick. Let's do that 0.1 centimeters again. Or sorry, 0.1 meter, 10 centimeter, and draw that cross section. Now you can see how it kind of gets, just more points and a little thicker. And coming from here to here, we have, again, doing the math, 1.771. And let's subtract off this lower yellow point, 1.840. So that's 6.9 centimeters. So right again at that 7 centimeter mark. So that's what I was finding on those edges. You look like you're getting about 7 centimeters on the flats where you don't have like a lot of overlap, or you're like in the middle of it. It's right at this 5 centimeters. The R3 Pro V2 was right at this 1.5 centimeters, basically everywhere, in the overlap, in the flats, everywhere across the data set. Okay, guys, now I want to look at a few other things that I found while investigating these data sets, and I think it's interesting. It's on the repeatability, and this actually draws into question where the data is accurate everability. So play with me here because I'm going to show it to you. I'm in this GPS time view of the L2 dataset. We flew the mission. We did overlap. And when you fly back over something, you get some very large mismatches. So look at these rooftops right here. This is the same roof, but you see here on the edge, this is a big mismatch. So it's like skewed. The data set is skewed. And then you'll see on this side how the green pokes through from the yellow. And so this is the LiDAR basically doing this in the X and Y. So it's moving this data left, right quite a bit. So, and I can come in here, we can just do a measurement from this point out to that point. Let's see. And so that's about 13, 14 centimeters there. So now I just measured this vertical error, but now we're looking at about 13 to 14 centimeters of error, you know, in this twisty motion, in the yaw, is what they call it. And so you have to compound the error in your vertical. You know, 13 centimeter, 14 centimeters is almost a half a foot. I mean, that's big, guys. That's big. So now, even if we do grab curbs, your curb could be, you know, yes, we have this 7 centimeter up down, and you have, or this, you know, 5 centimeters if you're not looking at that overlap. And then, but it also could be up to a half a foot off, you know, forward and back. So this was what I found very interesting, and I wanted to go in and play more because after seeing this, I needed to go out again. I needed to fly more. I wanted to fly at 120 meters to see what happens to this data set as we go higher. Because like we said at the beginning of the video, DJI said that you can fly up to 450 meters with this thing and get, you know, data back. What does it look like? Because now I'm starting to question things. I'm going to show you again just for comparison. Let me pop over to the R3 Pro so you can see what that same building, same rooftop. Here's the overlap. You don't see any mismatch on the edge of these buildings. So that looks, it's spot on everywhere. So this distortion doesn't happen in all LiDARs. You know, it's not like this is just a thing of LiDAR. No, this is in fact something that the L2 is doing. And there's one other metric inside their data sheet. They talk about this point, I think it's 0.01 degree, the gimbal rock. And I'm wondering if that's what's going on here. Is that gimbal moving, you know, a little bit, you know, jogging back and forth and adding this error into the data set on top of the IMU error already. Okay, guys, so now that we've, okay, this is the investigation. We went ahead and looked at the colorization. We looked at the caliber of the R3 Pro versus the L2. We looked at the precision of the points. We saw some about 1 to 1.5 centimeters on that R3 Pro across the data set. We found 5 centimeters to where that overlap is at, that 7 centimeters on the L2 data set. But then this stumbled upon us into this overlap issue, and that could potentially add an additional 14 centimeters, 13 centimeters in error to your data set. But I want to go ahead and run the optimize and the smoothing and then compare those and see what we're getting. The optimize, the best it's going to do, it's doing a computer vision model. It's just going to split the difference, right? So it's going to, it'll pull one to the other one and make a match, you know, so it's assuming one's right and we'll move the other one to it, or it's splitting the difference between the two and just moving them both to it. So is it actually getting more accurate? I don't know. Okay, guys, let's go ahead and jump into those data sets next and start diving into it. We're going to leave the R3 Pro V2 behind. I think what we saw was that it is accurate. It got great data. The colorization looked good, you know, so check. Now, so we won on the accuracy, but now we want to look at this range and we want to look at these things that we're seeing in the L2. So let's take a look at that and do a little bit more deep dive into that subject. Come with me. Now, welcome to part 2 of this L2 deep dive. After that first part, we wanted to really dive in deep and do 3 more flights, 120 meters. We did that 45 meters already, and the 30 meters. And we wanted to go ahead and process it, if you see over here, on the optimized, no smoothed, and optimized and smoothed, and to see what the differences are. And the results are pretty darn interesting. Let's do a quick deep dive in this, and I think this means I need to do another video on this. because I didn't expect this at all. So right now I have 3 datasets pulled up, all unoptimized, no smoothing. So it's 120, 45, 30 meters. All the same area, same base station, everything should be aligned perfectly. So let's go ahead and come down here. And what I have, he'll know which ones are which. The yellow was the 120 meters, the purple was the 45, and the green was that 30. So right here, I'm already seeing at 120 meters, it is incredibly fuzzy data. And this is of a hard, smooth surface. This isn't the second returns or third or fourth or fifth returns data coming back. This is just like that first return coming back. And what we're seeing is incredibly fuzzy data, 120 meters. Now, if you remember at the beginning of the video, I said the L2 was rated at 450 meters. What would it look like there if this is what 120 is? Why don't we go ahead and I want to go do a cross section and see what are we really looking at here. So let's draw a cross section, and I want to make this same 10 centimeters as before. Let's go ahead and show that. Now taking measurement on that 120 meters, we have this high point, and that is at 21.7. And let's subtract out this low point down here, 21.89. So that's about 19 centimeters of fuzz there. And 19 centimeters is about, let's go ahead and look at that. 19 cm to feet is about 0.62 feet. So over half a foot of fuzz on this 120 meters. Now, if we come back and we look at the 30 meters, we can see right here, this is that overlap section we're talking about. So I want to look at there first. And I want to look at 21.829. 21.829. And I want to subtract out this bottom one at 21.881. Well, that's 5 centimeters. Well, that doesn't seem right because we flew at 100 feet. Let me go ahead and measure a few more spots on this and see what we come up with. Again, I'm looking at the green. The green's the 30 meters. 21.830. Subtract out. I mean, these might be outliers, so let me zoom in and show you guys. These might be outliers, so let me grab this point. 21.864. About 3.4, so about 3.5 centimeters on that. So that 3.5 centimeters, that is a little over 1/10 of a foot. So this is at 100 feet. 100 feet, a little over 1/10 of a foot. And we already saw there was about 5 centimeters on that 45 meters already. So I went ahead and measured around this data set a bit, and the 120 meters I found a quite significant portion at this 20 centimeter fuzz thickness. And so that 20 centimeters is about 0.65 feet. Very interesting. But you might be asking yourself, hey, why don't you use the optimize and smoothing? And so I did. Let's go ahead and take a look at, again, this is the same data set, same area, same flight. I mean, the flights are right after each other. And let's take a look at what that looks like on the smoothed. Let's see what the effects are and the optimized. Okay, now I have the 3 data sets that are optimized and smoothed. We have the 30 meter in purple, 45 meter in green, and the 120 meter in yellow. Let's come back to that same area we're looking at before, and look what we find whenever we look at this. The optimizing algorithm actually chooses a point in the middle of the fuzz to move all the data to. So what's happening here is that you'll see these smooth data sets, but the actual accuracy is being pulled to some point that's not the actual true surface. And when I do a measurement here, this is about a 5 centimeter jump between this flat plane and this flat plane. So we're seeing about 5 centimeters jump between that 120 and that 30 meters. And it's not consistent. It does this differently across the whole data set. A few other things to note is right here, like just looking at the smoothing, this actually was a step right here. And it totally smooths across the step, and there's no step anymore. We have curbs over here we can probably more easy to see a curb and just, I mean, there's no more curb, guys. You can see there's a big just discontinuity in the data set. I think that's where a curb might have been at one point, but now it's totally smoothed off. So when you run the optimizer and you run the smoother, you're gonna lose a lot of details. Everything's gonna get smoothed off. No more curbs, no more steps, all gone. You know, little things that you park your car against, those little concrete things, those are gone now. And, you know, the running prevailing knowledge from people that I hear out there are saying, well, hey, I can still get a great topo off of this. But now we're seeing a tenth of a foot, you know, vertical separation in the smooth from just the same flight. You know, so I don't know. I think this warrants me going out and flying a bunch more. So what I want to do is I want to go fly, you know, the same area in woods. And I just want to fly it like 5 times in a row and see, will I even get the same surface again? So that's going to be in the next video. I'm also going to do more height studies and see what the effects of height is. Because if you have great range, but the data is total garbage, does range even matter anymore, is the question. Okay, guys, well, this was a long video, and I hope you guys were able to dive deep with me inside this data set and see some of the things I've been seeing. And ask yourself the question, you know, yes, the L2 is better in range than the R3 Pro, but if that range gives you bad data, does it even matter anyways? So, clear to see, accuracy, if you need accuracy, R3 Pro is going to be the winner. Yes, I do make it, but I just went out and flew these things, so I'd love you go do it too, and just also show me what you get. So it's all about educating. It's all about knowledge sharing. I want you guys to see everything I do. I'm going to share all the data sets. You'll be able to see it all. And I'll see you here next time here on Indiana Drones.